Okay, let's continue with this review. You also have to be able to name ionic and molecular compounds. You know they're ionic compounds by looking at what type of element it starts with. For instance, calcium here is a metal. There's a line here that zigzags down. To the left of it are metals. To the right of it are nonmetals. When it's to the left, you have a metal here. And we have a metal with a nonmetal bonded together, you have an ionic compound. Also, +1, +2, +3, skip carbon, -3, -2, -1, and that's how you know what charges they have. Calcium is right here, it has a +2 charge. Fluoride is right here, it has a -1 charge. Crisscross down, CaF2. Aluminum oxide. Alumina is here with a +3 charge. And oxide is here, oxygen, with a -2 charge. Al2O3. Both of those are already reduced, so I don't have to go any further. If the elements are in the middle here, they're transition metals. You need a Roman numeral to tell anyone what the charge is of that element. It is never ever ever telling you how many there are. It's telling you what the charge is, so that way you know what to crisscross. If it does turn out to be the same number, that's a coincidence. It has no other bearing. So copper is Cu. No, it's in the middle. So I need the charge. The charge they tell you is a 2. Nitride, +1, +2, +3, -3, -2, -1 is right here with a -3 charge. Notice I can look down the periodic table and figure out the charge, whereas I couldn't with copper. That's why you need the Roman numerals. Crisscross, Cu3 and 2. I knew to use the crisscross metal because copper is a metal. Crisscross method for ionic. Nickel is here. Once again, it's a metal. That 3 is telling me it's a +3 charge. Phosphide is right here. And it's a -3 charge. Crisscross. Notice 3 and 3. I can reduce that down to 1 and 1. So NiP. For molecular compounds, remember there's this line here. If it's on the right, it's a nonmetal. Notice that both nitrogen and oxygen are both on the right hand side. We have 2 nonmetals here. That's how I know I have a molecular compound. So here we use the prefixes, and that's telling you how many I have. So nitrogen, di is 2. Oxide is oxygen, and tetra is 4. No reducing, that's it. That's the bottom line. Iodine is here. Fluoride is here. They're both nonmetals. When it's mono for iodine, or when mono for the first element, you don't say it. You just automatically assume it's just 1. Fluoride, mono, is 1. Okay, capital B is here. Hydrogen is the exception. It is actually a nonmetal, even though it's in this row. So I have 2 nonmetals, which means I need prefixes. 2 is di, so diboron. 6 is hexa, hexahydride. Carbon, it's here. Even though it's 1, I'm going to leave the mono off because the first element is 1. Carbon, fluoride, 4 is tetra. So carbon tetrafluoride. So when to use which naming? You look at the staircase, the diagonal line. If it's on the left, it's a metal. If it's on the right, it's a nonmetal. Ionic is metal and a nonmetal bond together. 9 times out of 10, this is going to be true. There is an exception of ammonium, which is a polyatomic cation, but all the rest of the time it's going to be a metal. This is when you use the crisscross, and then you reduce it. If it's a Roman numeral, you know about that by the fact that it's in the transition metals. If you need to determine the charge of that, you uncross the numbers, the subscripts. Just like we crisscross to get the subscripts there, you can uncross it to figure out what the charges are. And always double check the anion. Alright, so molecular or covalent is nonmetal and nonmetal bonded together. And you're going to use prefixes. There are no tricks to that one. Alright, so Avogadro's number is the number of particles per mole. You use it when you see the words atoms, ions, molecules, or formula units. Be very careful of them because sometimes they'll be asking about atoms, yet they give you molecules, so you have to break it down. We'll do one of those. Avogadro's number is 6.022 times 10 to the 23rd particles per mole. It's a generic word particle, and that's because of the fact that it can mean any one of those four things. Alright, so 0.2 moles of H2O. You put your number you're trying to convert over 1. We have moles on the top, so we want to put moles on the bottom. Notice it's per mole up here. That means that's how many particles is equal to 1 mole. We're trying to figure out how many molecules there are. So I put 6.022 times 10 to the 23rd molecules on top. So 0.2 times that is 1.20 times 10 to the 23rd molecules. .450 moles of iron contain how many atoms? So, I see the word atoms, so I automatically say I'm going to need 6.022 times 10 to the 23rd atoms is equal to 1 mole as my conversion factor. Put the number I'm trying to convert over 1. We have moles on top, so I want to put moles on the bottom of the next one. That is equal to 1 mole. Multiply that across. Comes out to be 2.71 times 10 to the 23rd atoms. Calculate the number of hydrogen atoms in 1.058 moles of H2O. Alright, this is where it gets tricky. So if we look at H2O, we know that H2O is a molecule. So we use Avogadro's number to tell us how many molecules there are in 1 mole. So I can convert it over to molecules. In 1 mole of water, there's 6.022 times 10 to the 23rd molecules. But it's asking about specifically hydrogen atoms. So if I look at 1 molecule of H2O, so in 1 molecule of H2O, there are 2 atoms. That's why I want to multiply this one by 2. So 1.058 times 6.02 times 10 to the 23rd times 2 atoms of hydrogen for every molecule of water. That comes out to be 1.27 times 10 to the 24th atoms of hydrogen. Alright, so molar masses are pretty straightforward. All you want to do is look at the periodic table, figure out the mass of the individual elements, and then multiply it by the subscript because that's telling you how many there are. So carbon is right here. So I have 1 times 12.01. I have 4 hydrogens. It's right here at 1.01. Add those together and we get 16.05. That's it. We have 3 carbons, once again at 12.01. We have 8 hydrogens, once again at 1.01 by looking on the periodic table. Multiply and then add them together to come out to be 44.11 grams per mole. And then finally we have potassium, which is down here. We have 2 of them. And then we have 1 oxygen, which is right here at 16.0. And that comes out to be 94.2. Alright, so then we can use the molar masses to do conversions. So how many moles are in 12 grams of CH4? So 12.0 grams CH4. The moment you see grams, you immediately think molar mass. So that's your key term. Grams or mass, you use molar mass. So, mass. Atoms, ions, molecules, formula units, use Avogadro's number. Grams, mass, you use molar mass. So, I need to figure out the molar mass of CH4. We figured that earlier at 16.05. So we have grams on top, so I want to put grams on the bottom. 16.05. And then that's 1 mole. Divide that out. 12.0 divided by 16.05. 0.748 moles. Alright, so let's do another one. 2.85 moles of C3H8. I see the word grams, so I immediately look on the periodic table to calculate C3H8. 44.11. So I have moles on top, so I want to put 1 mole on bottom. And then the 44.11 grams goes on top. So that way the moles can cancel out. Multiply that across, comes out to be 125.7 grams. And finally, we want to know how many potassium ions. I see the word ions, so I immediately think, okay, I need to use Avogadro's number of K2O, which is a formula unit. It's not an ion, but we can get to ions. By saying that there are 2 potassium ions in every 1 formula unit of K2O. I also see grams here. That means that I'm going to need the molar mass of K2O. This is a much more complicated one, if you haven't gathered it by now. 94.2 grams per mole. We already calculated that earlier. So, put the starting number over 1. Just take it one step at a time. You can do this. Don't get overwhelmed. Okay, so here's our starting number. We have grams on top. We want to put grams on the bottom. So, because of grams, we want to look at molar mass. 94.2. Okay, we use that one now. Now we look for moles in the other conversion factors, and there are none except for this one down here, the middle one. For every 1 mole of K2O, there's 6.022 times 10 to the 23rd formula units. Okay, we've used that one now. So for every 1 formula unit of K2O, there are 2 K ions. So it's going to be 15 divided by 94.2 times 6.022 times 10 to the 23rd. Remember, when you put in this calculator, it's EE. So 6.022 EE 23, then times 2. That comes out to be 1.92 times 10 to the 23rd ions of K. Make sure you know how to use your calculator and know how to put that times 10 into your calculator. Because if you actually type in times 10 or times 10 23, you're going to get it wrong. You don't want to do that. Alright, so balancing. How I like to do it when I'm beginning is I want to look at all the elements I have. So I have N and I have Cl. I have 1 on the left, 2 on the right, 3 on the left, and 2 on the right. So we take it from the beginning. We have 1 and 2. In order to get this one to equal 2, you have to multiply it out in the front as if you were doing it in algebra. Like if you had x plus 5, you would multiply that whole thing by 2. So these coefficients, that's what these are called, are multiplying that entire compound by that number. So we no longer have 3 chlorines on the left. We now have 6, which means I need to multiply this by 3. We have manganese, oxygen, hydrogen, and chlorine. I'm going to give you a little helpful hint here. Notice on the right hand side you see chlorine in 2 different places. That tells you to keep that till the end. Do that at the very last one to balance, because a lot of times they'll just fall into place and it'll make your life easier if you don't stress over it at the beginning. So manganese we have 1 and 1, oxygen we have 2 and 1, hydrogen we have 1 and 2, and chlorine we have 1 and we have 2 here and 2 here for a total of 4. So manganese are balanced, oxygens are not. We have 2 and we only have 1 over here. If I multiply the water by 2, that gives me 2 oxygens, but it also messed up my hydrogens in the process. So I now have 4 hydrogens on the right, because 2 times 2 is 4. Alright, nothing else got messed up in the process, so I can keep going. So I look over here and I see I have hydrogens. I need to put a 4 out in front of that in order to balance that out. This then messed up my chlorines, because I now have 4 times 1, which is 4, which actually makes the chlorines on the right balanced. So we're good. And then the last one, Al, C, H, and Cl. We have 4 aluminums, 1 on the right, 3 on the left, 1 on the right, 1 on the left for hydrogen, 4 on the right, 1 on the left, and 3 on the right for chlorines. So we have 4 aluminum here. We need to get 4 here, so I'm going to multiply this whole thing by 4. This changed my chlorines. I now have 12 chlorines. It didn't change anything else. Carbons, we have 3 here. We have 1 on the right, so I'm going to multiply that whole thing by 3. That changed my hydrogens to also be 12. It didn't change anything else. So hydrogens, I have 1 here and I have 12 over here. So if I multiply HCl by 12, that changes my hydrogens to 12. It also changes my chlorines to 12. And that makes it balanced. Alright, so types of chemical reactions, you're going to be able to look at a chemical reaction and identify it as one of these different types. I'm going to show you what to look for. Combination are when multiple things are coming into one thing. So for combination, you have one item, one compound, or whatever you want to call it, on the right. Decomposition is things breaking up. This is one compound on the left. This is what you want to be looking for. Take the time to look in your book and do a couple practice problems so that way you know you can identify them. Like, oh, okay, I see what you're talking about. Single replacement is an element and a compound. Double replacement is compound plus compound. Do not get wrapped up in semantics. If the question says something like AB plus C and it says compound plus element, you still have an element and a compound on one side. So I'm actually going to write that in here just to make sure that you don't get caught up on little things. And then in combustion, you're reacting something with oxygen. For us, we're going to focus on carbon-containing items, compounds. So it's going to make CO2 and H2O for a complete combustion. So that's what you're going to want to look for, is CO2 and H2O. Now redox. Know your definitions. If you lose electrons, it's being oxidized. If you gain electrons, it's being reduced. You remember that? I remember it by Leo Gurr. Lose electrons, oxidized. Gain electrons, reduced. Another set of definitions which is more biological focused. If you gain bonds to the oxygen, oops, that's supposed to be an L, or lose bonds to the hydrogen, it's being oxidized. Whereas if you gain bonds to hydrogen and lose bonds to oxygen, it's being reduced. So if you gain bonds to oxygen, it's being oxidized. Now redox. To do redox, what you have to do is figure out what the charge is at the beginning and at the end. And I look at it as a number line. So here's 0. Remember, electrons are negatively charged. So if you gain electrons, it's going to equal more negative. If you lose electrons, it's going to be more positive. Because when you gain electrons, you're gaining more of a negative charge, so it's becoming more negative. If you lose electrons, you're losing more of the negative charge, so losing a minus gives you a positive. Alright, so look at the elements and match them up. Chromium's going from a +1 to a +3. It's becoming more positive. More positive is losing electrons. And then remember Leo Gurr. Lose electrons, oxidized. So this one's becoming oxidized. Tin is starting at a +4 and it's going down to a +2. It's becoming more negative. More negative is you gaining electrons. Gain electrons, reduced. If it starts off as an element, it's 0. So that's 0, that's 0. And then when it's bond, it goes to the oxidation numbers. So chlorine becomes a -1. Acetylene becomes a +3. I know that because of this 3 here. Put the AS together and put the CLs together. AS goes from a 0 to a +3. So it starts at 0 and it goes to a +3. It's becoming more positive, which means it's losing electrons. Lose electrons, oxidized. Chlorine's going from a 0 to a -1. It's becoming more negative, which means it's gaining electrons. Gain electrons, reduced. Notice that every time you have one, you automatically have the other. So once you find one, the other one's the same. Sodium's a +1, bromine's a -1, chlorine's a 0. Sodium is a 1, chlorine's a minus 1, bromine is a 0. So sodium did not change. We're looking at the bromine and the chlorine. Bromine's going from a minus 1 to a 0. It's becoming more positive, so it's losing electrons. Lose electrons oxidized. Chlorine's going from a 0 to a minus 1. It's becoming more negative. More negative is gain electrons. Gain electrons reduced. And that's how you do redox. And the last thing we're going to discuss is stoichiometry. Once again, don't get overwhelmed by this. Take it one step at a time. I like to do it as a very visual thing. How many moles of Na2 S2O3 are needed to react with 0.12 moles? Remember the coefficients out in front, these numbers out in front, even this invisible one here, are all relating to moles. So the moles of one compound to the moles of another. So because of that, we have to get the unit in moles before we can do anything. This is already in moles, so I can immediately use the coefficients. So put the number I'm trying to convert over 1. Notice I immediately put what compound I'm referring to. If you don't, you're going to get lost. You don't want that to happen. We have moles of CO2 on the top, so I want to put moles of CO2 on the bottom. I'm going to need coefficients to go from one to another, so 4. I have an invisible 1 here, so I'm going to put 1 mole, because that's where I'm heading for. And I'm actually looking for moles, and I have moles here, so I don't even need this next bracket. So it's 0.12 times 1 divided by 4. And that's it. Notice also where you're coming from is on the bottom, where you're going to is always on top. That's another way you can look at it. Let's do a more complicated one. Oxygen gas can be produced by decomposing potassium chlorate using the reaction below. If 138.6 grams of KClO3 is heated and decomposes completely, what mass of oxygen gas can be produced? Before I even start, I'm going to glance at the equation and I notice that it's not balanced. So before I do anything else, I want to balance it. Always double check that your reaction is balanced. Okay, now that it's balanced, I can start making my plan. I have grams of here, and I need to go to grams of here. However, I need to get it into moles before I can do that. So grams to moles. In order to go from grams to moles, I need the molar mass of KClO3, which happens to be 122.6. You figure that out by looking on the periodic table. Look at one potassium, 1 chlorine, and 3 oxygens and add them together. Now that I'm in moles, I can go from moles to moles by using the coefficients. Coefficients are only for that horizontal line. Notice I did not multiply the molar mass by 2. That 2 does not come into play until the next step. And then from moles to grams, once again I need molar mass because I see the unit grams there. But this time I need molar mass of oxygen, which happens to be 32.0 grams per mole. Alright, so let's set this up. The number we're trying to convert is 138.6 grams KClO3. First thing I want to do is convert it over to moles. I need to go from here to here. So grams are on top, so I need to put grams on the bottom. I know I have 122.6 in 1 mole. Notice I'm not getting lazy with my with identifying what element I'm talking about, what compound. Okay, so now I'm here in my plan. I need to go from here to here. So moles, I'm going to use the coefficients now. The horizontal line tells me coefficients. Always, 100% of the time, if there's a horizontal line, it's coefficients. To 3 moles O2. I'm right here now in my plan. I need to go from moles to grams. So in 1 mole of O2, there's 32.0 grams of O2. What you're looking for will always be in the top of the last bracket. Grams of O2. So 138.6 divided by 122.6 times 3 divided by 2 times 32.0. Multiply that out and it becomes 54.3 grams of O2. And that is everything you need to know for the first exam in Chem 119. Study really, really hard.